Hello, and welcome to my next session in the Modern Java by Example webinar series. What we're going to do today is revisit the very first example we looked at and do a much deeper dive on how the parallelism mechanisms in Project Reactor work. And unlike before, where we primarily just looked at the code, this time we're going to do an inspection of how the operations are actually behaving with respect to the concurrency and parallelism that they have going on behind the scenes. So without any further ado, let's go ahead and share the screen and we'll get started. So I'm going to share my screen. First, as always, let me show you where the code is from. So this particular set of code is in the RxJava folder under the ex2 folder. So this is the source code we'll be looking at. This version has changed quite a bit from the version that we looked at a couple weeks ago when we did it before. So as I said, when we did it before, we primarily looked at the way that streams and parallel streams worked to download images. And now we're going to take a very deep dive on how the parallelism mechanisms in Project Reactor work under the hood. So without any further ado, let's launch into the main program. So here's the main program. I've restructured it just a little bit. First and foremost, of course, I've added support for Project Reactor as well as RxJava, as well as Java parallel streams. So there's three different mechanisms. We're going to primarily focus on Project Reactor today, but I'll also show a little bit of the parallel stream stuff. Project Reactor and RxJava are pretty much equivalent in terms of the capabilities and performance that we would expect to see from a parallelism point of view. So here's the main program. We come in here, we warm up the thread pool, and then right now we're just going to run the reactor tests. If we uncomment these other lines, we'd also run the RxJava and parallel streams tests. And we might do some of that a little bit later, but let's start out with the RxJava stuff. So as you can see, we're going to run a bunch of different tests. We're going to run a test showing flat map, and we're going to run it both with the concurrent fork join pool as the thread pool that we're using for the scheduling of the threads. And then we're also going to use it using the parallel pool, which is the one that comes out of the box configured by Project Reactor itself to run things in parallel. Then we're also going to run some parallel flux examples. And again, here we're going to run a couple different variants. We're going to run one example that uses all the cores available on my computer, which in this case are essentially 4 hyper-threaded cores, so effectively 8 virtual cores. And we're going to use the common fork join pool for that. Then we're going to go ahead and run it with all the cores enabled, except this time using the parallel pool, which is the default. And then we're going to go ahead and run the implementation with just a single rail in our parallelism model. And I'll explain more about what a rail is in the context of parallel fluxes when we get into the code a little bit more. And for this example, I used the common fork join pool, but I could have used parallel just the same. Okay, so let's go ahead first and just take a look at the runtime performance. I ran these things a little earlier because they take a while to run. It's very bandwidth and network bandwidth intensive. So I ran this test and I downloaded 10, I guess it was 8 images here. So everything should be running basically in parallel. And you can see here that the version that used flat map and with both parallel and common fork join pool were roughly about the same. And in fact, these were also very similar to parallel flux using the common fork join pool and using parallel. Now, had I run it with more images to download and had I run it over a faster network, we probably would have seen a little difference, but they're all about the same. The main thing to notice here, however, is that using only a single rail of parallelism will definitely slow things down. And that's because we're only taking advantage of one core in that case. And when we look at the code, you'll see exactly how this works and why you probably wouldn't want to do this particular approach unless your goal is to artificially restrict the amount of parallelism that's available for whatever reason. You might want to be conserving the other cores in your platform for some other processing, some database processing or other types of IO intensive or compute intensive tasks. So that just kind of gives you a high level view that all these different versions perform roughly the same. And the more parallelism you throw at the problem with respect to the number of cores you use, of course, the faster the performance. So now let's go ahead and take a look at the run flat map implementation. And you're going to see some interesting things here. One of the things I've done here is I've got some really cool logging mechanisms that we're going to show off. And these will make it really crystal clear how the different concurrency and parallelism mechanisms in Project Reactor behave under the hood. And I think this will be fun because it'll teach us a lot of interesting things about the different features and the different ways you combine the features and the way in which different scheduler pools have an impact on the overall system behavior. So here is our run flat map test driver. We reset the garbage collector. We delete the downloaded images. And then if the log flag is turned on, we run the test download flat map log method. Otherwise, we just run the test download flat map method. And you'll see the difference is interesting. And I couldn't quite bring myself to have a common piece of code for both of these things. I ended up splitting them up into two fairly similar but not identical pieces of code. So this is what we're doing with the non-instrumented version, the non-logging version. This is kind of the production version, if you will. So what we do is we go ahead and we get the list of URLs using the from iterable factory method. It's part of Flux. We then use the flat map idiom, and that should say the Reactor flat map idiom, not the RX Java flat map idiom, although it's the same thing. And then for each URL, we're going to go ahead and emit this particular URL using just. We then subscribe on whatever scheduler was passed in, which could either be the common fork join scheduler or the parallel scheduler, or it could be the elastic scheduler or the immediate scheduler. There's a bunch of schedulers you get, or even a custom scheduler if we chose them. And once we've done the subscribe on, we then go ahead and do the map call. And you'll see when we look at the instrumented version in a second that has logging turned on, that where you put the subscribe doesn't really matter. You get the same behavior. So subscribe on is essentially position independent within a pipeline of operations with Project Reactor and RX Java for that matter. What we then do is we go ahead and we take this flux of files, because we used flat map, so we end up with a flux of files, and we call collect list. And collect list is a bit like the collector capabilities that are in regular Java, in Java streams. And we end up with a mono to a list of files. And when that completes, we go ahead and take the list of files and print out the size of the list of files, signifying what was downloaded. And as you can see, we block until we're done. So that's the code without logging enabled. Let's now go take a look at the logging code. And this is really neat. So here's the logging code. What you see I've done is everywhere I want to see what's actually happening under the hood with respect to concurrency and parallelism, I've inserted a doOnNext hook method call. And doOnNext is just kind of a call that is used to inspect whatever's happening. And in this case, we kind of log it, but it doesn't change the output. So we're just going to return, we're going to keep the output going along, and we're just going to kind of peek in there and do a little bit of logging. So you can basically think of doOnNext as kind of like peek in Java streams, if you're familiar with that. So we start out the same way. We get the iterable, and now we've got a bunch of choices. For the first go round, we're going to go ahead and do the actual call in the calling thread. So we're going to get all the iterables from the calling thread. And just for kicks, to make this all more clear, let's just go back quickly to the program, and let's comment out everything here except for one of these tests. So we can actually run this with instrumentation turned on, and you can see the behavior that I'm about to talk about, because I think it'll become really crystal clear as soon as I do that. And let's also go up here to the edit configurations window, and let's turn logging on. So now we're going to log. And for this particular example, I'm going to make life really easy. We're going to have only 3 images we're going to be dealing with here, as opposed to 8 or 10 or 40 or whatever. I go up to I think to 42, but we're not trying to drown us in an output. So let's go ahead and go back to the code here, and let me just run it, and then we can talk about what we're seeing more precisely. So when I run this code, you can see some interesting things. This is the code, this is the result we get. So these little log identity methods I've instrumented the code with, we'll look at what they do under the hood in a second, but what they basically do is they print out the name of the thread where the computation is running, and then they also print out the computation itself, and then they print out whatever the item was that we were working on. So you can see in this particular variation of this, we're getting all the data from the calling thread, which in this case is the main thread, and we're going to get images 1, 9, and 10. So those are the 3 images we're going to get. And then you can see everything else is going to run in the common fork join pool. Now, if I replaced the common fork join scheduler with the parallel scheduler, it would all come out of the parallel pool. And I'll show you that shortly, just for kicks. But you can see that everything else after we get the first three elements is coming out of the common fork join pool. And you can also see the matching that's going on here. So you can see, for example, that image 9 is emitted from worker thread 3, and then you can see that it's processed by worker thread 3 through the map call. So what that says is there's an affinity here, and when we get the thread, when we get the URL and emit it out of the just call, the mono just call, that starts in worker thread 3, and then it continues to be processed in worker thread 3. So that's actually what we want. You'll also notice that, so there's a lot of parallelism going on here, but then finally when collect list gets called, only one of the threads, probably the last one that's standing at that point, it's the one that is going to be processing after collect list is done. So we only need one thing at that point, because it's basically joined everything down to a single mono to a list. Okay, so armed with that as knowledge of what the behavior of the program is going to be, let's kind of come back here and then look and see what's actually happening. So here you can see mono, just, and then we are going to go ahead and log the URL and the fact that we're calling the mono just method. So you can see that ran in a worker thread from the common fork join pool. Then we put the subscribe on call here. Now this is kind of interesting because subscribe on can either go here, or we could also comment out this code and we could put subscribe on after map. So we can either put subscribe on before map, or we can put subscribe on after map. And the thing I want you to notice, first, just a quick recap. This is what it looked like the old way with subscribe on coming before the call to map. And here's what it looks like when we put subscribe on after the call to map. And lo and behold, the output is the same. So what I'm saying here is that it doesn't matter where subscribe on goes in the pipeline here, as long as it stays within that particular pipeline. It doesn't matter whether it comes before map or after map. It has the same impact on the behavior of that particular little piece of code. Keep that in mind, because when we talk about parallel fluxes and the run-on method that's used to identify what scheduler to use to run the various elements with the parallel flux, it does matter where that goes. So subscribe on is kind of position independent or position agnostic, whereas run on is not going to be position independent and position agnostic. So just come back here and we'll just turn it on here and comment it off there. I kind of like it. I think it makes it more sense if it goes earlier, because it just underscores the fact that it's going to be on for the whole time, but it doesn't really matter where it goes. You can see that we then go ahead and collect everything using collect list, and then you can see that the collect list logging operation only ran in a single thread. So that's clearly merging together the various elements that were running in parallel, and we end up with a single thread that handles that. Okay, so that's basically the way things work for this particular run. But now let me just do a little few tweaks and show you some other cool stuff. So what I can also do, I can go back up to the top here and I can make from iterable run in a different scheduler. So if I do this, now you can see that I've gone ahead and done subscribe on for whatever scheduler happened to be passed in. But now it happens, and it's going to affect from iterable. So let's go ahead and rerun this code again, and you'll see the output. So if you recall before, the from iterable calls were all done in the main thread, really just the calling thread, whoever called this function. Now what happens when we do that, that subscribe on call is those iterable calls will now be done on a different thread from the calling thread. So now we've moved this off the calling thread. And that's a classic example of RxJava or Project Reactor's ability to make calls move off the calling thread and thus become asynchronous. So in a way, that's kind of a bit like the supply async call in completable futures that we talked about the other day. So notice, however, that we're still using the common fork join pool for everything here. Well, now for kicks, let's go over and let's comment out this code. And let's instead turn on this code. And this code is going to also subscribe, but rather than using whatever scheduler happened to be passed in to the test download flat map log method, instead we're going to use the elastic scheduler. So let's see what happens there. And this is kind of cool. It shows the infinite malleability of Project Reactor and of course RxJava. So now you can see that we're getting the iterable out of the elastic thread. And the elastic thread pool is something like basically a cached thread pool with the Java executors framework. It doesn't start with any threads to begin with. Every time a request comes in to an elastic thread pool, either a new thread is created if there are no free threads, or if there is a free thread, that thread is reused, and threads time out if they're idle for more than a minute. So that's what the elastic pool does. And also, just for kicks, just to make this demonstrate even more flexibility, if we come back up to this example and we comment out this code here, this is the code we're running right now. Notice that this code is the code that uses the common fork join pool. And we're going to replace this code with the code here. And this is basically the flat map code, except this code is using the parallel scheduler, not the common fork join pool. So if we run this, then what we should see is that we're going to get from iterable out of the elastic pool, but then all the other computations take place out of the parallel scheduled pool. So you can see how easy it is just to tweak these things and mix and match the behaviors. And once again, you can see the affinity where when you do adjust, it starts out initially in one thread, and that continues on through the map. So once you've done that, it sticks with the little pipeline of calls. Now, of course, we could change that behavior too, but that's probably too much concurrency for its own good. So we're going to keep it there. So that's just a little walkthrough of how things behave with respect to using the flat map idiom. So let's now go ahead and comment out the flat map code. And instead, let's go ahead and take a look at some of the parallel flux code. And this is going to be really interesting too. Same idea. We're going to turn logging on, and we can play around with whether we want to use the common fork join pool, whether we want to use the elastic pool, whether we want to use the parallel pool. All those things can be done. So now we're going to go ahead and run the parallel flux code. So let's run that, and then we'll go look at the logged version of this code. So you can see there's a bit more logging going on here because I was able to instrument it more thoroughly, and we'll see how this all works. So once again, this is just kind of give you the big picture view. Now let's go ahead and look at the code, and we'll come back and look at the output here in a second. So we go back over to Reactor tests, and we go down to the parallel flux tests. So before I show you the instrumented code and how it works, let me just walk through what the implementation is going to do. So as before, we take a function with the file to download and save, the name of the test, the level of parallelism, which could be basically all the cores or one of the cores or whatever, and then whatever scheduler we want to use. So those are the same parameters we essentially passed to the flat map version of all this. Once again, we start out by doing from iterable, and if we so chose, we could do a subscribe on for that. Might be overkill, as we'll see in a second, but it's certainly something we could think about. And then what we're going to do is we're going to use the .parallel operation. And there's a method defined on a flux called parallel, and it converts a flux into a parallel flux, as the name implies. And you can give it the desired parallelism level. If you don't give it anything at all, it defaults to the maximum number of cores known by the virtual machine or by the execution environment. In our particular case, we're going to tweak this, so we're going to pass in an explicit number, which is either 1 or 1 core or the number of cores. And of course, we could do anything between those two numbers if we chose. It doesn't really do you much good to make more than the number of cores. You could do it, but it won't do you much good. The next thing we do is we go ahead and do the run on call. And this says, for that level of parallelism that we just requested for this parallel flux, go ahead and execute that parallel flux in this pool of threads. And again, so there's really two dimensions here. One is the thread pool mechanism, which is what run-on defines, and the other is the amount of parallelism, which is what dot parallel defines, what the parallel operation defines. And in this case, they could really be different, and they are different in this case. So we're using the common fork join pool. I take it back. Since we're using the common fork join pool, if we give it the max number of parallelism, it's going to be the same number of threads as in the common fork join pool. If we were doing a different scheduler, like the elastic scheduler, then in that particular case, it could be different. You could have the elastic scheduler have more or less numbers of threads than the number that was given here. Okay, so we're going to show you when we get down to the debug version of this, the log version, that where you put run on really matters for parallel. Doesn't matter, the subscribe on stuff doesn't really matter for fluxes, but putting run on in the right places in a parallel flux will have a big difference in terms of how it behaves. So I'll show you that in a second. So we're going to go ahead and run things on the scheduler. The documentation for Project Reactor talks about what's created by the parallel call as the number of rails. So think about it as basically a rail being kind of a track, if you will, or a flow where all the computations will run, in one thread in parallel with other threads. So this is clearly intended for embarrassingly parallel tasks, such as the ones that we have here. What we do then is we go ahead and map the download and store image function, which we'll go ahead, as we'll see in a minute, and run them all in parallel. And then we do basically a join. And this is a little bit interesting. When you look at this in a second and look at the debugged log version, it's really quite interesting what happens when sequential is called. What it's effectively doing is it's converting the parallel flux back into a sequential flux by joining all the parallel rails into a single rail. So think about like a switching station at a railway yard where you've got a bunch of tracks that then have to come and be single tracked for some period. Same basic kind of idea. We take that flux and we collect it into a list, and then we go ahead and print the results. So that's basically what's happening. Now let's go ahead and take a look at the version that has the logging in it. So the first thing we're going to do is we're going to go ahead and do the from iterable, and we're going to log what thread things are running on at this point. And if you go back to the output from the run, you can see that all the from iterables are all running in the main thread of control. And then you'll also notice that some of the other code is running in the main thread of control too. And so let's show what that is. In fact, you'll notice that all the calls to parallel are also running in the main thread. So we can see that we're going to do parallel here. And in this particular case, we then log what thread parallel is running on, and it's also running in the main thread. And that makes sense because we're just setting a field basically to indicate the number of rails. And then run on gets called. And run on is what then actually turns things over to run in parallel on the given scheduler. So when we do the run on method and we go back and look at the output, you can see that run on, now once run on is called, now we're actually running in different threads in this case in the common fork join pool, but it could be the parallel pool, the elastic pool, or whatnot. So run on is going to be running in worker thread 7, another run on in a different rail is running in worker thread 5, and yet another run on is running in another worker thread, this one being worker thread 3. And this concept of running on something continues down into the next calls in this pipeline. So if you go and look at the code here, you can see that after we do the run on, then we do the map, and then we go ahead and log what thread map is being called in. And you can see that map is being called in these threads in the common fork join pool. And again, as we had seen before for the other version, there's this affinity that's going on here. It's kind of hard to see it from the output that's coming because it's a bit verbose. But essentially what's happening here is that we're able to keep the affinity. So what's run on for a certain thing will then go ahead and map on the same thread. So there's an affinity of that thread, which is exactly what you want to minimize context switching. And then before I give it away, you'll notice also, interestingly enough, that all the calls to sequential also take place in different threads in the pool. So sequential is really a call that starts the joining process together. So it's kind of like a thread barrier, if you will. And so when we get to sequential here, all of those calls are still running in different threads, but what they're doing is they're all being joined together. And then when collect list gets called, when we look at collect list, you'll see that collect list is going to only have one thread running in collect list. And you'll see that the way it seems to work is whatever one gets there last is the one that takes over and is the one that does collect list. And that's also pretty much what you'd expect. So when threads get done with their processing and they come up to a collect list, it acts something as a barrier. It probably drops the results off in some kind of buffer or variable or whatnot, or queue. And then the last thread that comes through there is going to say, aha, I'm the last thread. I'll do the collect because everything's been collected at that point. And so you can see that it runs on the last thread that arrives. And that's basically the same way things worked with the flat map idiom for the other version we looked at for Project Reactor. And again, you can see that at that point, we collect everything up and we're done. So I think that's quite interesting. But let me show you why run-on matters. So just kind of keep an eye on where these things occurred. You can see there's lots of parallelism going on here. If we were to go over here, however, and we were to move where run-on was defined, so run-on is now defined after map, not before map. Let's take a look at the output that we get in that case. And so look at that. Look at how interesting that is. What's happening on here? What's happening here is that we have hardly any parallelism going on at all. In fact, it's actually bizarre parallelism. So everything is run sequentially. We do all the processing in the main thread. We do the mapping, the download and storing behavior in the main thread. And then we do the sequential operation in multiple threads, which is completely bizarre because there's nothing in parallel at that point. And then you can see that we end up basically doing collect list and bringing them all back together again at the end. So this is clearly not what you would want because we've completely gotten rid of any ability to have this thing running in parallel in a meaningful way. But it just goes to underscore the point that the placement of run-on in a parallel flux has a significant material impact on the behavior of the program with respect to concurrency. We end up with the same results, of course, either way, but in this particular case, the concurrent or the parallel behavior, the threads they're running on are quite different. Okay, so let me show you one more quick thing here, and then we'll take some questions. I decided to have some fun, and I did the same basic instrumentation with the Java Streams implementation as well. And this is also quite instructive. So if we come over here and we go over to the main program, let us comment out run reactor tests, and we'll uncomment run stream tests. And then we go over to run stream tests. And what you're going to see here is we've got a bunch of tests that we're showing off. So I'll just go ahead and run them. I probably should only do one of these, but you'll see that they all behave pretty much the same with respect to the points that I'm trying to make. So let's take a look. Here's the point I'm trying to make. So let's first go and look at the code, and then we'll talk about what the code means. So where's the log version? Here's the log version. So this is the parallel streams implementation of the downloading program. And I think you'll see a couple things. First, you'll see it's just a bit more concise than the Project Reactor version and the RX Java version, because parallel streams are really baked in nicely to Java streams. So it's real trivial to make a parallel stream. So here we're going to go ahead and get a list of URLs. We turn it into a parallel stream. We then go ahead and log what thread that's running in. We then go ahead and do a map operation, which of course in a parallel stream will be running on different processor cores, as we'll see, different threads. We do another log operation, and then we do the collector. And just for kicks, I instrumented the collector also. So everything is instrumented out the wazoo here. So I instrumented the accumulator phase of the collector, and I just printed out what's going on. So let's go ahead and look at the results here, which are really instructive. If you're a longtime follower of my channel and my discussions, you know that I've often pointed out that with parallel streams, the size of the common fork join pool is one less than the total number of threads. And the reason for that is that the caller pitches in and is used for the duration of the call as one of the threads that's used as part of the thread pool. And this example here really demonstrates that quite nicely. So let's go ahead and show the part that matters. So this is the code that's the one of the various parallel streams tests. And you can see what happens here is that the parallel stream calls are actually being done in 3 different threads. So this is another indication of why streams work so nicely, because parallel stream itself is going to be running in different threads because it's all part of the wonderful parallel splitterator features built into Java. So you'll notice that we'll be doing some parallel stream decomposition in worker thread 5, in worker thread 3, and in the main thread. And that's because the main thread's pitching in when we're waiting to collect. It's pitching in. The calling thread is pitching in and being used as part of the pool. Then you can also see that the map call here is being done in 3 different threads, 2 threads out of the common fork join pool, and the other thread is the main thread, so that's pitching in there as well. And then you can see that that accumulator method that's part of the collector is also running in 3 different threads. So again, collect is being run in 3 different threads, and then the final collect is triggering all the processing. And if we were to go and look carefully and do some further instrumentation of the final finisher phase of this code, you would see that that was also being done in the main calling thread. So hopefully that illustrates a bunch of cool things. It shows how parallel processing is so interestingly woven into streams, and it also shows how the main thread pitches in and helps out along with the other threads in the common fork join pool. Now, I didn't actually go to the trouble of instrumenting all the RxJava stuff, but had I done so, I suspect it would have been pretty much identical to what we saw with the Project Reactor code, because the parallelism mechanisms for RxJava and Project Adapter are essentially equivalent. But if you're curious, you're welcome to go and play around with this. You also might want to play around with it and add additional log statements, various places to kind of see what's going on under the hood. But I thought this was a good starting point to show the key things I wanted to get across. Let me also quickly, just for fun, show you that logging method, which I stuck over here in my options class just to put it someplace easy to get to. So here is log identity, and this particular code, as you can see, takes a generic element and an operation. It prints the current thread name, prints the operation, and then prints the element. So that's where we got the results. Okay, so with that, let us go ahead and stop the discussion, and I will be happy to take questions. Let's see. Oh, there we go. So a couple questions. These are good questions. Does do next always run in the same thread of the previous operation? So yes, in the particular way that I'm using it, yes, it's going to run in the previous operations thread. Is parallel flux like a parallel stream? Sort of. You can think of it like a parallel flowable. Parallel flux is very much like a parallel flowable from RxJava. So if you're familiar with RxJava and the concept of a parallel flowable, a parallel flux is pretty much identical to a parallel flowable. It's not quite like a parallel stream in the sense that it is not so transparent. The minute you commit yourself to being a parallel flowable or a parallel flux, you're moving into a slightly different realm of available operations. It's a restricted set, and it's a subset really of what's available to a normal flux or a normal flowable. So it's a subset. Whereas with parallel streams, as you know, the operations, the intermediate operations, and the terminal operations you can do on a stream are pretty much identical to the ones you can do on a parallel stream. So it's not quite the same semantically, but it plays a very similar role to a parallel stream. There's another question too about, do custom pools support work stealing? Only if you implemented it yourself. So work stealing, to my knowledge, is only provided by the common fork join pool, or fork join pools in general. And I don't believe that the other pools that are provided by RxJava or by Project Reactor support work stealing. So like the parallel pool or the elastic pool, I don't believe that they support work stealing. And of course, why would they? They can always use the work stealing mechanisms in the fork join pool to do the work stealing if they need to. Implementing a work stealing thread pool is really complicated. If you've ever looked at the source code for the fork join pool in Java, you'll know what I mean. It's very complicated. So no one in their right mind would re-implement that if they could use something off the shelf. What will be the issue if we call collect list without calling sequential in the case of parallel flux? That's a good question. Let me show you, because I think it's easier to show you than to describe it. And I think what you will find, because I know I've probably tried this at various points, if we don't do sequential, I just don't think it's going to compile. And that's because there is no collect list method defined on a parallel flux. The collect list method is only defined on fluxes. And so if you don't convert the parallel flux to the flux with sequential, then it simply isn't going to do anything. So, I mean, it won't compile. There's some other things you can do with parallel fluxes. There's this thing they have a method called collect. But what collect does is it basically allows you to give a collector for each rail. And so what you'll end up with when you're all said and done is basically a group of collectors that are collecting the contents of each rail. And I haven't really found a good use case to motivate that. There's my understanding that there's things called flux groups and so on that can be used to do the processing. I haven't found an example yet where I need that, but it's available as one of the other features. So bottom line is that you probably would not want to, well, you certainly can't call sequential, you can't call collect list on a parallel flux without first sequentializing it. What's the difference between parallel and common fork join pool? Well, the most obvious difference is that the common fork join pool supports work stealing and parallel does not. In fact, let's go over here and we'll look at this also quickly as well, because it's kind of fun. Share the screen and go back to my IDE and we'll go to the main program. So whenever you find yourself wondering something like, I wonder how this method works, the obvious thing to do is to do something like this, uncomment the code so it's visible, and then go snoop around in it. So if you snoop around in parallel, which is the factory method that's used to create a parallel or create something that's parallel, you'll see that this is going to make a parallel scheduler. And the way it works is it goes and looks up the scheduler in the cache. And these are a bunch of either enums or other things that keep track of different properties. So we have cached parallel, parallel, and parallel supplier. And if we look up here, we'll find those fields defined somewhere. I guess I should follow my own advice and just do this and go find them. So you can see that cached parallel is an atomic reference to a cached scheduler, and parallel is basically a string that says I'm the parallel guy, and parallel supplier is, in this case, essentially a supplier that goes ahead and makes a new parallel. And you can see it makes a parallel, which is the name. It makes it with a default pool size. Wonder what the default pool size is, just for kicks. So you can see default pool size is either going to be some system property or it's going to be the number of available processors. So if we go look at new parallel and peek down there, you can see that new parallel calls another helper method that's going to take a Reactor thread factory that's going to give the threads a name. So if we follow down here, you can see that we're kind of in a twisted maze of interlocking callbacks, we finally end up here to a parallel scheduler. And here's what a parallel scheduler is. And it's in the parallel scheduler class. And it says scheduler that hosts a fixed pool of single-threaded scheduler executor service-based workers and is suitable for parallel work. And so if you look at this, you can kind of see how it works. And it uses the scheduled executor service. It looks like they have, different scheduled executor services for each element here. I haven't really looked through this code in a great deal of depth yet, but you can see that they initialize this by creating a bunch of scheduled executor service instances that are part of this array. And I'd have to read it in more detail. But one of the things I think that's worth noting here is this is definitely not using the common fork join pool as far as I can see. I think under the hood, they say that they're using fixed sized, it's basically a fixed sized set of these scheduled executor services. So if you're curious and want to look around at this some more, feel free to poke around. But my experience was it was certainly not using the common fork join pool. And honestly don't really know why they went to the trouble of making their own. They must have found some reason that they wanted to be able to have events that are time-based events working with this as well. Let's see. If the position of run-on is after parallel, then the parallel behavior is not guaranteed. I'd say it's more than not guaranteed. It's just not going to happen. So where you place run-on semantics are like publish-on semantics in Project Reactor, which are the same as observe-on semantics in RxJava. And what they do is when you publish on or observe on or run on something, the parallelism or the concurrency starts at that point and continues down until you change yourself to something else. And that's very different from subscribe on. So subscribe on, first of all, you really should never have more than one subscribe on in the same pipeline because only the first one wins. So even if you try to change your mind later, it's just ignored. And whenever you do a subscribe on, as you see, it kind of starts from top and goes all the way down to the end of that particular pipeline, if you will. So subscribe on and publish on or observe on have different behaviors. They can be used for different purposes. Rail is like a splitterator. Not really. Splitterators basically create tasks that are then thrown into the common fork join pool for execution by any available thread in that pool. And in fact, they could be stolen by threads in that pool. A rail is really more like a particular, it's sort of like a dedicated virtual thread upon which all these operations in that rail are going to run. So it's not quite the same concept, but what it's getting you is efficient, embarrassingly parallel processing. I guess that's probably the best way to look at it. Okay, so as usual, these are great sets of questions, and this is really what I wanted to cover today. What I think we're going to do tomorrow is I've got some other things to cover having to do with different ways of using parallel streams mechanisms and streams mechanisms in general. And I want to kind of talk about some of the issues of using splitterators, ways of using collectors and so on. So I think tomorrow that's what we're going to talk about. And I've been learning some other more advanced features of Project Reactor. And hopefully at some point also we'll be able to demonstrate some cool examples that use the web flux framework. I've been working with Sanjeev on this, and so we'll hopefully have something to demonstrate there, which will be fun because then a lot of the examples will be more realistic and more like actual reactive applications, not just single process, single address space examples, but ones where we can actually run different servers in the background and have them serve the data up at different rates. So if there are no other questions, thanks to everybody for coming, and I will look forward to talking to you soon.